we're going to focus on what are called optimization problems. So in very simple terms, we are trying to find the best solution to a problem. Now, best is really vague, so what do we mean when we say best? Usually, we are talking about finding a minimum or finding a maximum to something. So the idea here is that we're going to be taking real-world problems, translating them into mathematical form, then using the techniques we've learned from calculus to come up with the best or optimal solution. And as you've seen before, this is going to involve minima and maxima. So to help us through all of these problems, because they can seem somewhat overwhelming, I'm going to give you a procedure for how you should go about studying each one of them. Now, this is very similar to the related rates idea, where every problem's a little bit different, but following this procedure will help you get a better handle on things and help you develop confidence, because you'll have a single approach to try to tackle every one of these problems. So as always, we want to draw a diagram, right? Picture. Can you take the written information and translate it into something visual? It really helps you understand what's going on. At this point, we want to talk about variables. We got to label our unknowns and list off any given or known information. It's really important to define the variables properly, because the details that follow from there can be overwhelming if you're not clear on what it is all of these symbols represent. The third one is finding a function. We need a one variable function for the quantity that we're interested in. Now you might say, well, how can you have more than one variable? So you'll see as we work through these problems that many variables will come up in step 2, and they will all enter into the function that you create. We only know single variable calculus. We haven't yet gone beyond, so we don't have the techniques to handle multivariable functions all at once. An important part of the solution process is understanding the domain of your function. And what's important here is the domain an open or closed interval? If it's a closed interval, we can use the ideas from chapter 4.1 and the closed interval method to figure out an absolute minima or maxima. If we have an open interval or even an infinite open interval, we need a new idea to find the minima and maxima. I'll mention that in just a moment. Once we've got the domain settled and we have our plan of attack, then it's time to differentiate. We're going to need to differentiate to get the critical values and then classify the minima and maxima. And this will follow very closely with what we do in chapter 4.3. Once we do all the hard work in the differentiation in step 5, we've got to come up with a conclusion. All of these problems you're going to be given are in sentence form, so you're going to want to give your response in sentence form as well. So it's something that I'm hoping you will take and incorporate into your working process here. This procedure is going to help you keep all of the details straight. I mentioned up here that if you have a problem with an open interval, you may need to do something different. So I'll briefly talk about that here. We are going to be talking about a special case of finding absolute minima and maxima. And this is going to be just an extension of the first derivative test on open intervals. And so the idea here is that if your function has only one critical point, so it has to be a point in its domain, where the derivative is 0 or doesn't exist. And if there's only one on your open interval, so then the situation is either you've got your first derivative being positive to negative, or your first derivative going negative to positive. If this is the case, if you have only one critical point, that means if you're going from positive to negative first derivative, this must be the absolute max. There are no other points. It's always going up and then switches to always going down. Now, similarly, if your function is always dropping until you get to that point and then always rising afterward, this has to be the absolute minimum. Remember that these are critical points. So they are points in the domain of the function. There is actually a point there. So I'll talk a little bit about this second case. I'm going to go through an example where you've got this second case, and I will walk through the procedure at this point.